Hello, this is Dennis Derrickson. I'm a professor at California Polytechnic State University in San Luis Obispo, and I'm in the electrical engineering department. Today, I want to tell you all about thermal noise, and then I'm going to end that presentation with an actual measurement of thermal noise using the Keysight SSAX source signal analyzer. So let's first start by talking about what is thermal noise and where does it come from. So first, we're going to start out with a cross section of a resistor here. So here's a resistor, here's an ohmic contact on the left and an ohmic contact on the right. And I have two instruments measuring properties of that resistor. I have a voltmeter that's measuring the RMS voltage across the resistor. And I have an ammeter that's for measuring the current that goes through this resistor. There is no external source applied. I'm going to measure the inherent noise that's found in a resistor, and that noise is called thermal noise. Okay, let's look at this electron right here, E minus. Now, it is free to roam inside the resistor body. And this type of resistor body I have here is made out of silicon, and it has N-type material, meaning that electrons are the primary carrier that are free to run around that. And so this is resistive material. And so this electron right here will move with thermal velocity, and it will go a certain distance, but eventually it will collide with the lattice of the resistor, and then a new electron will be created by thermal generation. It will move again, and so we got this jerky motion of this electron that's being created, and it gets recombined, it's created and recombined. So on the average, that electron goes nowhere. But if you look at this dashed line right here, and if I'm a little tiny person the size of the resistor at the molecular level, I will look at this resistors and say, you know, if I count the crossings of this electron back and forth across that dashed line, I swear that looks like an AC current. AC current means that the current is going to the left for a while, to the right for a while, back and forth. So this random electron motion with no net motion across a certain line right here represents an AC current. And so if you were to take a very sensitive voltmeter, you would find that there's a voltage across this resistor, because the voltage across the resistor is the current times the resistance. And there will also be current flowing in this resistor. And so that is a fundamental source of noise in all electronic systems. Now, here I show that this collision happens right here, where the electron will collide with the lattice, and the average time between these collisions in silicon is about every 0.5 picoseconds. It will travel for a while, and then it will collide with the lattice. A new electron will be generated. It will go for a while, be colliding another half picosecond later on average. And so how fast are these electrons traveling? So what we can do is a calculation from physics that the kinetic energy of an electron in a electron gas inside this substrate, this resistor, is 3/2 times kT. K is 1.38 times 10 to the minus 23 joules per second, and temperature is measured in Kelvin. So the units of that is joules. That's the kinetic energy of an electron inside this resistor. Now, if we equate that to the kinetic energy of a particle, which is 1/2 mv squared, where m in this case is called an effective mass, which is close to the actual mass, but usually somewhat less. And especially for electrons, it could be 10% of the actual mass, depending on the material. If you equate these two and solve for velocity, you'd find that the electrons, when they're going through this path right here before collisions, are going about 2.3 times 10 to the 7th centimeters per second in between their collisions. So this person is right. He sees that electrons are going back and forth across this dashed line. There's a current that forms, and that is a measurable quantity, and that's a fundamental limit to the sensitivity of many electronic systems. Now, we can come up with a circuit model for that noise, and if we do that, what's the resulting equation is shown here. If you have this resistor, this would be a perfect noiseless resistor, and we're going to add a series voltage source, an AC voltage source. And the value of that AC voltage source caused by thermal noise is the square root of 4 times K, 1.38 times 10 to the minus 23rd joules per Kelvin, times the Kelvin temperature. Let's use 209 degrees Kelvin for room temperature. The measurement bandwidth. So anytime we do a measurement, we don't have infinite bandwidth. So we always have to know what bandwidth that measurement is done in. And then the resistance. This is called the Thevenin equivalent model for resistor and its thermal noise properties. And if we have a Thevenin equivalent, we can also form a Norton equivalent from circuits. And so in a Norton equivalent, we have the same value of resistance, but now we have a current source in parallel with resistance. And the Norton current source has an RMS value of square root of 4kTb divided by R. So in summary, we have a N-type material with electrons going randomly back and forth, but a net go nowhere. And we have a noise source that you can measure with a really sensitive voltmeter, or you can measure that with a really sensitive ammeter. And at the end of this presentation, we're actually going to demonstrate a measurement of these parameters. Now, this was an N-type material where electrons are the carriers. You can also have a P-type material. So here in the P-type material, let's say we have a silicon P-type material, the primary carrier is now a hole. And just like electrons, holes can move and they can collide with the lattice and have thermal noise. So both hole motion and electron motion can contribute to thermal noise. And depending on the type of material you have, one may be stronger than the other. And if we do the same calculation saying that the kinetic energy of a particle is 1/2 m effective times velocity squared times the average kinetic energy, we can say that for silicon, they travel a little slower than electrons, and the average velocity between collisions is 1.6 times 10 to the 7th centimeters per second. This person says, yep, they're not electrons this time, they're holes, but they're going back and forth, and they're causing both a voltage across the resistor and a current across the resistor that have the same values that you found if it was an electron traveling in this resistor. So let's look at the quantity associated with this, just plugging in numbers. So 4kTb divided by R would be the Thevenin equivalent current of this resistor. And let's look and put two resistors in parallel. We have R1 resistor and R2 resistor. They're in parallel. And I want to answer the question, the noise source associated with R1, how much power does it deliver to R2? Let's also make the assumption that R1 equals R2, so we have maximum power transfer. So in that case, we're going to take the current in this resistor R1, and since R1 and R2 is a current divider, half the current is going to go into its own resistance, and half the current will go into the other resistor R2. We want to find out how much power does that resistor deliver to that resistor right there. And if I put that, if I take the amount of current in resistor 1 and divide it by 2 because of the current divider, I square it times R, that will give me the power in the resistor 2. And if I multiply it all out, I just get this expression KTB. So if I choose different values of the bandwidth from 1 hertz to 1,000 or 100,000, this is 1 megahertz right here, I can see how many watts we have. I can put it in decibels by taking 10 log of the power in watts to get decibels compared to a watt right here. And if I want to add 30 dB to that number, I can get decibels compared to a milliwatt. Now, this number you see right here is oftentimes quoted in thermal noise as minus 174 dBm of power in a 1 hertz bandwidth. So that's probably the most common metric that people use for thermal noise, minus 174 dBm per hertz. That's how much power resistor 1 delivers to resistor 2 if they're the same value resistor. So a very important constant, minus 174 dBm in a 1 hertz bandwidth. So in the world of circuits, sometimes we talk about real resistors, like those axial lead resistors with 2 leads, and you look at their codes on them and find out what value resistance they are. But there are other kinds of resistance we talk about in electrical engineering, and another one is called an AC resistance or AC impedance. So Z is the impedance, which is a complex number. It has both real and imaginary part, or magnitude and phase. So a common AC resistance that you might encounter is you might have an antenna, which is a half-wave dipole. So this is just a wire right here, and it has a length of 1/2 wavelength at a particular frequency. And we can use a instrument called a vector network analyzer. And this is an example of a vector network analyzer as part of the Keysight F5058 SSAX source signal analyzer. And between these two terminals right here, we have a vector network analyzer that can cover from 0 to 50 gigahertz. So if we looked at the resonant frequency of this antenna right here, we might find that at some frequency that it has an impedance of 50 ohms plus J0 reactance. And so you might say, okay, that antenna has a 50 ohm resistance. That's an AC resistance. But the key thing is that inside this antenna, there's just perfect conductors. The coaxial connection to it, the antenna, there's just a 0 ohm. There's really no resistance associated with this. But if we do put power into this coaxial cable, we do get power that's radiated into space. And so we have an effective input impedance of 50 ohms that represents the impedance that allows the input energy to go into space, but it's not a real resistor. So this antenna does not have thermal noise, even though with this network analyzer, we're going to measure an input impedance of 50 ohms. It's not a real resistor, and there's no resistance anywhere in the system. There's a radiation resistance that's 50 ohms, but it has no noise. So I wanted to differentiate between a real resistor, which has thermal noise, and an AC resistor right here that, in this case, has no noise associated with it. Now let's look at other viewpoints of thermal noise. So let's look at an oscilloscope. An oscilloscope measures on this axis the amount of voltage. On the horizontal axis, we measure time. And so if we had a 50 ohm thermal noise source and we put it into a perfect spectrum analyzer that had great sensitivity, a perfect oscilloscope that had great sensitivity, we would, every time we do a trace right here, we would get a little different voltage versus time waveform. And if we collage them on top of each other, we'd find a whole series of voltages. And if we do a histogram on this AA cross section right here, and just show what's the voltage at that point in time over many, many, many traces, we'll get a histogram display. And the most common voltage would be 0 volts, but there's a positive voltage probability and negative voltage probability, and that's going to be measured by a Gaussian distribution, which is shown right here. So if I had an example, a resistor that was 50 ohms and it had 1 megahertz of bandwidth, and I plugged that into the formula and assume a Gaussian distribution of noise, I get a plot that looks like this. So the most probable voltage on this cross section right here will be 0 volts. But at any point in time, it could be at 1 volt or 3 volts, not very probable. This is probability in this axis right here. Could be as much as 5 volts, not very probable. Excuse me, this is units of microvolts. Could be as high as 5 microvolts with a small probability. It could be 1 microvolt with a significant probability, or -3 volts with a smaller probability. But in an oscilloscope, you can see the noise versus time. And if you do a cross-section histogram, you can plot the statistical probability of a voltage. And so all those viewpoints, the time domain viewpoint, the probability domain viewpoint, are all different ways of thinking about thermal noise and its different personalities. Now let's look at the spectral domain view of thermal noise. So in a spectrum analyzer, you have noise power on your vertical axis, and you have frequency on your horizontal axis. Now I repeat this measurement of, depending on the bandwidth, how much power do you have in thermal noise in dB, in regular watts, in dB watts, or in dB compared to a milliwatt. Remember, -174 is that magic number that we all remember about thermal noise. Now, in a spectrum analyzer, one of the adjustments you have is called the resolution bandwidth. And that's the width of a bandpass filter that is used in front of a power meter on the spectrum analyzer. And so if we had a 1 megahertz resolution bandwidth, which would be right here, we'd have a minus 114 dBm noise display. Now, if we just go onto our spectrum analyzer, instead of typing in 1 megahertz for the resolution bandwidth, we typed in 0.1 megahertz, we would find that the displayed noise level will drop by 10 dB. Because noise doesn't have a specific frequency, it's white. It has energy that goes from DC maybe to infinity. Well, it seems that might be impossible, but it's broadband over most of the frequencies we care about for electromagnetic communication systems. Now, would this white noise continue out to 100 gigahertz? Would this white noise continue out to 1,000 gigahertz? So that relates back to that average time between collision. And since we have a half picosecond time between collision, we're going to have this white noise go well beyond the hundreds of gigahertz range into the low terahertz range as white. And then beyond that, it will change somewhat. But the key thing I want to show right here is that it's white noise. And since it's not a particular frequency, the more bandwidth you have for observation, the more noise you have. And if you take the spectrum analyzer, just type in different values for resolution bandwidth, then the noise floor will scale up and down with how wide of a filter you have in front of the spectrum analyzer. So that's the spectral domain of white noise. Now, I'm going to go through an example here where you can get a sensitive receiver that can actually measure the voltage noise as a function of frequency from a 50 ohm resistor. And so this instrument right here called the Keysight SSIX, the source signal analyzer, has an input right here called the baseband noise analyzer. It's a very sensitive receiver covering from 10 millihertz up to 10 megahertz. And with this input, we can actually measure the thermal noise of a resistor directly. Now, I want to talk about how this is done in the block diagram of the SSIX baseband mode. So we're going to have an input noise source. In this case, it'll be a 50 ohm resistor. And that 50 ohm resistor will be divided into two identical amplifier chains, channel 1, channel 2, but they're going to be identical in all aspects. We're inputting noise to here, but we'll have channel 1 and channel 2 that have their own noise. And channel 1 noise and channel 2 noise have no relationship with each other. They're random and they have no magnitude or phase relationship with each other. So the signal right here at the input, which is going to be our 50 ohm resistor, will be applied to both of them. So the signal will be amplified through channel 1. And our signal here is thermal noise, and our thermal noise will also be amplified from channel 2. Channel 1 and channel 2 will add their noise sources to that, but they will have no phase relationship with the baseband noise. Then we're going to put it into an analog to digital converter, and we're going to get an output in the frequency domain. So at the output of the A to D, after the fast Fourier transform, we're going to have noise voltage at different frequencies coming out of that box right here. And then we're going to do a magical thing called the noise cross correlation activity. And the noise cross correlation activity is going to allow us to cancel out the noise in channel 1 and channel 2 and only see the noise that's input at the input. And so that's why we're able to see the thermal noise. So let's look at the block diagram and see how that is accomplished in a graphical illustration right here. When you go to the SSIX baseband noise measurement system, it just shows a device under test, which is noise, a AC coupling capacitor right here, which you can change, and then it has variable gain. In our case, you can go from 0 to 50 dB. But actually, inside, there's actually two parallel amplifiers, which I'll show you in a second. Okay, here's my block diagram of what's happening inside this really sensitive system that can directly measure thermal noise from a 50 ohm resistor. So we'll start out with our 50 ohm resistor, and at one point in time, we're going to represent it as at one point in time in one particular frequency of the noise, you will have a vector, and that vector is red, and that's going to have some magnitude and some phase. And so I'm going to arbitrarily say at some point in time, at some frequency, I have 1 volt with angle of 45 degrees. And so that's going to go into these two amplifiers. We're going to split equally, and each of these amplifiers is going to amplify the signal. In addition to amplifying the signal, channel 1 and channel 2 will both add their own noise. And so, but the noise is not correlated to the input 50 ohm resistor noise. Here I show one that has a half of a unit amplitude and a phase of 125 degrees. And I show this one is 0.5 amplitude, phase of minus 980. And these are constantly changing, but I'm choosing a point in time and a certain frequency that's happening right here. So we go into this analog to digital converter and an FFT operation. And so output of that's going to be, we're going to have different frequencies off each channel because we did a Fourier transform. And then we'll have the input noise right here from the 50 ohm resistor at some frequency, plus the channel 1 noise right here. On the other channel, we're going to have the input noise plus channel 2 noise at a particular frequency. And they're going to be, we do a full trace, we do the FFT, and we're going to have magnitude and phase that come out of this FFT. And so here I show the red signal, which is the input 50 ohm thermal noise. And then I show that the channel 1 has its own noise, which has thermal noise and other noise components. And it's going to add with a certain phase at that frequency. And then you'll get this resultant blue vector right here, which is adding the 50 ohm noise resistor plus the channel 1 noise resistor to get this resultant vector right here. On channel 2, we're going to have the 50 ohm noise amplified again, but we'll also have this internal channel 2 noise, which is in a different direction, and we'll have this vector here adding together. When we add the vectors at the output, we're going to get this resultant right here, which is going to be 1.2 angle of 80 degrees. That's a vectoral sum of the thermal noise plus channel 1 noise. And then we'll also get on this side right here, we'll get the vector sum of the noise in the 50 ohm resistor and channel 2 noise right here. And then we're going to do this cross correlation at that particular frequency. We're going to take the channel 1 noise at that frequency, and we get the channel 2 noise, but we're going to do something called a complex conjugate, which is essentially flipping the phase from a positive phase to a negative phase. And we're going to multiply them together. And when we do that, in this particular instance, we get this vector right here, which is 1.08 volts in amplitude and 60 degrees. Now, it's not exactly the right value as the input noise, but given the fact that the noise we had in the channel was like 0.5, it's still, there is some noise suppression right here. Now, if we do this many, many, many times, many, many correlation operations, eventually we can essentially cancel out all the noise of channel 1 and channel 2, as long as the gain is identical. And the phase of the gain may be changing, but as long as the gain of the two channels are identical, we can cancel it out with this cross correlation technique. And we're going to do a whole bunch of them. So let's look at an example measurement. We're going to take a 50 ohm resistor and put it into this architecture where we split it into two, Fourier transform it, and do all these correlations. And let me show you a couple things. So on the bottom, what I did is I put a short circuit, a 0 ohm resistor, into this system. And a 0 ohm resistor has no thermal noise. And so this represents right here kind of the measurement floor of the system here, going from 10,000 hertz to 10 megahertz. So that there should be no noise with if you do enough correlations. And here we're doing let's say we're doing 20 million correlations, and that's where our noise floor ends up. We're canceling out a lot of the noise in the amplifiers. But the moment we go from a 0 ohm resistor to a 50 ohm resistor, then the signal trace goes up right here. So we are directly measuring the thermal noise of the resistor. It's definitely much bigger than the correlated noise right here with 2 million correlations right here. Now, if I do the measurements in dB volts, 1 hertz bandwidth, then we should get around minus 182 dBm, excuse me, dB volts in a 1 hertz bandwidth. And indeed, we get something pretty close to that in this system right here, around minus 182 dB volts. We're directly measuring the noise that comes from that resistor. Very sensitive receiver here. Now, at the lower frequencies below 1000 hertz, you can see it starts rising. And there's another phenomenon called 1/f noise, which I'm not going to get into. I'll do that in a separate presentation. But 1/f noise is another phenomena that's very important in noise systems. But from here at a couple thousand hertz up to 10 megahertz, we're directly measuring the thermal noise. Now, for other people, it might go, oh, wow, that's not such a big deal. For me, understanding noise, and I just am thrilled to see that we have a measurement system that's capable of directly measure thermal noise across a resistor. Very fantastic. I then went to a case where I had the same measurement. I just wanted to show that minus 181 dB volts per hertz is the same as minus 174 dBm of power per hertz. And so this is the same measurement without all the other annotations I had. I feel that I hope that you learned a little about thermal noise right here, what it is, seeing it in the time domain, in the probability domain, and the spectral domain. And I showed you how you can actually measure thermal noise directly with this correlation receiver. And here is a person right here celebrating the fact that I was able to measure thermal noise in a 50 ohm resistor with this measurement system, and that's fantastic. Such a small signal, and being able to measure that is very impressive. And that's my tutorial on thermal noise today, and I'll be going on to other noise sources shortly, but thanks for sitting in there with me.